11.1 Systems of Equations. Hopefully this is mostly review. We do need to look at some vocabulary though as well. So we're most familiar with systems when it concerns like two lines, what we have for example here. And we have different types of systems. So the first system would be when the lines intersect, the equations have, the system, sorry, has one solution, and that would be the intersection. So the intersection right there is the solution. And then it says this system is consistent and the equations are independent. So that would be called the description of the system. So if I ask you to describe a system, then here you would say consistent. And the word consistent implies that it does have at least a solution. Could have multiple, but it has a solution. And independent here refers to the fact that the two lines are independent of each other. Okay? Independent. I'm talking right, sometimes my spelling gets to be really bad. Okay. There's a second version that we could have here. If the lines are parallel, then there isn't a solution, and that means that we would call this an inconsistent system. Alright, and then the third one would be when we have two lines that are on top of each other, and then that would be that there are infinite solutions. Well, because there are solutions, we still are going to say that this is consistent. But then we distinguish from the first situation by saying that the two lines here are dependent. And hopefully that makes sense a little bit. So independent means two separate lines, dependent means the same line. So the same y-intercept, same slope, independent, definitely a different slope. Alright, what we have over here then are the rules for obtaining an equivalent system of equations. So basically this says these are the rules that we play by. And with play by, I mean these are the kind of things that we can do to solve a system algebraically. So we can interchange, so you can list the first, you can change the order in which you list things, you can multiply or divide all of the parts, and you can add or subtract. And that's what is given to us there. Okay. And then on your sheet you have something about Khan Academy, because I'm going to go through this a little bit fast. So in Khan Academy you get you a little bit more help if you need to. So solving a system. So for example, 2x minus y equals 13, negative 4x minus 9y equals 7. So how can you solve this? Well, let's multiply the top one by 2. So this is one of the rules up there. You can always multiply. 4x minus 2y equals 26. If we have the second one now listed below it, then you can add, and 4 plus a negative 4 is 0, and a negative 2 minus 9 is a negative 11y, and 26 plus 7 is 33, and then divide, so we know that y is equal to a negative 3. And if y is a negative 3, we can replace, for example, in here, and then we would get 2x plus 3, so move the 3, so that means that 2x is equal to 10, so x is equal to 5. So the solution, in this case we often state the solution as a point, because we are sort of think of this as two lines that apparently intersect, 5, negative 3. And the description here would be consistent and dependent. So the system is consistent and dependent. Alright, let's look at this one. 3x plus 6y is 12. So multiply everything here by 3. So 3, 6, 7 times 3 is 21. Let's subtract. 3 minus 3 is 0, 6 minus 6 is 0, and 12 minus 21 is a negative 9. Well, 0 does not equal a negative 9, so this is a system that does not have any solutions, so no solutions to the system. So that means that this is an inconsistent system. So two lines that were parallel. So the last one will probably have two lines that are the same, so 6, negative 9, 4, and 6. So I'm going to multiply this one by 3. And then I'm going to multiply this one by 2. 3 times a negative 4 is a negative 12. 2 times 6 is a positive 12. So 18x minus 12y is equal to 24. Negative 9x. Oh, I need to multiply the second one, right? Negative 9 times 2 is a negative 18x plus 12y is a negative 24. And then when you add over here, because we want to cancel the x's, everything else cancels as well, so we get 0 equals 0, and that is true. So that means that there are infinite solutions. Infinite solutions. And so infinite solutions, then the description would be consistent, because we do get answers, but we have dependent. Alright, if this is the case, then we often rewrite it by solving for one of the variables. In this case, both of the... Alright, so let's backtrack a little bit. So what this means is that we actually really have one line here. And so what I'm going to do now then is take either one of the two, and I'm going to write this in terms of just one variable, or solve for one variable. So let's look at this one. Maybe I should just do this, because I'm probably confusing you a little right now. Okay, so I'm going to solve this for y, because usually if it's a straight line we write y equals. So we would get 6y equals 9x minus 12. Divide by 6, 9 over 6 is 3 over 2. And then negative 12 divided by 6 is a negative 2. So this system, the solutions to this system, can be summarized by this sentence here. So this would allow us to generate the ordered pairs that would provide all the answers to the system, right? That's just the straight line that the system represents. Okay. Well, we can do that with 3 variables as well. And when you do it with 3 variables, you get definitely different pictures. So I try to show the pictures to you. On yours, the color isn't nearly as nice, so hopefully this looks a little bit better. This is what you know often happens. So this is a consistent system that has only one solution. With 3 variables, we often are dealing with an x, a y, and a z, right? Okay, so this has only one set of x, y, and z that will work for all 3 of the... Well, what do we have here? We don't really have lines anymore here, right? So if 2 variables give you a line, does it make sense that 3 variables basically, geometrically speaking, will give you a plane? So this represents a plane. And with this, I mean the x, the y, and the z represent a plane. Okay, you can have 3 planes that all intersect on one line, that is infinite solutions, or you can have the same plane 3 times over, just in different forms. And then, so these are the 2 situations now that represent a consistent system, but with infinite solutions. And then if you take 3 sheets and stack them like this, even though these 2 meet here, the orange one does not meet here. So there isn't one single point where each of the 3 planes has exactly the same x, y, and z. Okay, and clearly we can also stack the 3 planes on top of each other with a little space, and then they would not intersect either. Alright, so let's do one of those in context. So in context, we often see it in terms of quadratics. Just realized that I think I changed this on you guys' sheet, but this is no longer what we want. I want the following 3 points. I want it to go through -1, -14. Sorry, -1, -4. I'm copying now from my notes. -1, -4, 1, 6, and 3, 0. Alright, so I'm going to solve that system. And I'll need a little more space probably. So, okay. So how am I going to do that? Well, here's the structure of a quadratic, right? So let's fill in a -1, -4 and see what you get. So that means the y is a -4, -1 squared is 1, plus a -1 times b is a -b. That's sort of ugly, so let's just write that as minus b plus c. If I use 1, 6, then the y value that I have is 6. 1 squared is 1. 1 times b is b, and just 1c again. And then the last one, 3, 0. You get 0 over here. So 3 squared is 9. 9a. 3 times b is 3b plus c. So here's a system with 3 variables. So how do you solve this? Well, first you eliminate one of the variables twice, and what that means you'll see here in a second. So let's look at these 2. If I take these 2 and if I add these, and hopefully you will see that this -b and b are going to cancel. And that should just give me an a and a c something over here. So a -4 plus 6 is 2. 1a plus 1a is 2a. negative b plus b cancels, and 1 plus 1 is 2. And then actually I can make this even a little bit easier. I could write this as 1 equals a plus c. Okay. Well, if a plus c is 1, we can use that here in a minute. Alright, so I said a moment ago we're going to eliminate this variable twice. So I did this with the first two. So let's take the second two, and I'm going to write the 6 over here right away. So 6 plus a plus b plus c. And what if I take that one and do this now with it? And I'm going to subtract here. So I get 6 minus 0 is 6. A minus a negative 9 is a negative 8a. B minus 3 is a negative 2b. And c minus c is 0. Alright. This is a somewhat untraditional one, and I'm sorry. Your book will have plenty more examples, and I should have followed my train of thought here. So I am going to take this a plus c, because over here it says a plus c is exactly 1. So that I could write as b plus 1, and that means that b is actually 5. And so once I have b, and since I now eliminated c over here, I can write this as 6 is equal to a negative 8 minus 2 times 5. 6 is a negative 8a minus 10. So if I add 10 over here, I get 16 minus 8a. So a equals negative 2. And if a is a negative 2, then let's plug in b, 5, and a negative 2, and let's plug that in here. So I would get 6 is equal to a negative 2 plus 5 plus c. So 6 is equal to 3 plus c. So that means that c is equal to 3. So my final answer here would be that the quadratic that contains those 3 points is equal to y equals a, which is a negative 2, x squared, plus b, which is 5x plus c. And that quadratic is the answer that I was looking for. Okay, I would definitely check the book for some more of these. So check your book for some more examples on how to solve a system with 3 variables. And then Khan Academy has help as well. Thanks.